Hi, Chem 181 class. My name is Alexa, and I am going to go over chapters 1 and 2 so we can start reviewing for your exam. Let me just get started pulling my whiteboard up. Okay, here we go. To start off, I'll let you know that there is a Quizlet folder, and I will continue to build on that and add to it throughout the semester. Right now, I have quizzes for the units, mass volume and temperature conversion factors, and the di and polyatomics that you'll need to start retaining. These links will be emailed to you, so if you'd like to stop the recording and review those, feel free, but I'll also be reviewing this video. First, I'm going to talk about Sig Figs and scientific notation. I'll also go over those di and polyatomics. And I'll finish up covering solubility. And at the very end of this video, I'll also go over some problems that were a lot like on your last quiz. So let's get started. So first, let's review our Sig Figs. And so to start off with, if you're given an amount that is exact, like 1 pencil, or I think one example was like if you had 28 dozen notebooks, if you have something that is exact like this, then it technically has an infinite number of significant figures. Unfortunately, we won't be dealing with those mostly in lab. What you're going to be dealing with is something more like this, where you're going to be given data and you have to figure out what parts of it are significant for you. And the basic rule is that you have your leading zeros that are before your main part, and these are considered not significant. You have your zeros that are between non-zeros, and these are definitely significant. And then you have your trailing zeros, and these are also considered significant. These are considered significant because they are specifically to the right of this decimal point right here. So remember to keep that in mind. After you take identify your significant figures, usually you have to convert them into scientific notation. And scientific notation is putting your data into something that is greater than 1, but less than 10, and it's raised to a certain power of 10. Now, if you take your number to the right, for instance, like for this one here, this would be 4.0500. Technically, you are raising it to the negative of that many places. This is because when you look at it, the number is actually much smaller than how it really appears here. So this would be 1, 2, 3. If we were doing the opposite and we were given something like and we have to move the decimal point to the left, then what we are going to do is raise it to a positive power of 10. You are raising it to the bigger tower because the number is actually bigger than how you think it is. So for this would be 1, 2, 3, 4, 5. Okay, and when you're figuring out what the significant figures are at the end of your calculations, this is an image I found. I thought it was extremely helpful because you have different rules depending on the operations that you're doing. If you are doing addition or subtraction, you're going to be looking at in the data that you're given the amount of decimal places that are in that data, and that is going to help you figure out how many decimal places are going to be needed at the very end. So for this one had 1 decimal place, this one had 0, so you're going to need a figure that has 0 decimal places. In this one, with subtraction, you are going to be given something similar. So this, and with multiplication and division, Instead of decimal places, you are going to be looking at the significant figures in each piece of data. Okay. Next thing to go over are those diatomics. For your exam, you need to know 7. And diatomics are elements that occur in nature as 2 atoms. They are always going to be the same element, and it is a non-metal. And the link that's bonding them is covalent. So you have oxygen, which is the most common, and then there are 6 others that you need to know, and there are 2 different tricks that I'll go over here. One is the kind of the title Honkelbrief. And then there's another device where it's have no fear of ice cold beer. So whichever one helps you, add that to your notes. I'm going to switch over because now I'm going to briefly go over the polyatomics. Okay, here we go. Here is our table of polyatomics, and you not only need to memorize these, but also start to understand why they're in the columns they are. I found it most helpful to focus on the relationships that are going on within a column, like here with your chlorates, and over here in the chromates, and then also what's going on what relations are building across the columns with the phosphates. This is another table. This was on page 44 of your textbook, and this starts to just going a little bit more on some of the naming as you get more to nomenclature, the reasoning behind this. 8 is an ending that you'll use within a group of an oxygen that's built with the rest of the polyatomic, and that's the most that title is given to the highest number of oxygens that's within that group. So for your NOs, the 8 is going to go to an NO3, and the ite is used for the least number of oxygens that are going to be in it. So for this case, it's going to be the O2. For sulfur, it's a little bit different. The highest is going to be with 4, has a sulfate, and the lowest it can have is 3. And over here with your chlorines, you have this. So hopefully that'll help keep it when you come to memorizing those. I'll go back to the whiteboard. Okay. We're also going to look at physical properties of solubility, and as you probably remember, properties can either be physical or they can be chemical. And as you probably remember, features within physical properties, these can be intensive or extensive. And intensive is the same regardless of how much you have. So that would be things like odor, color, magnet attraction. And your extensive properties would be things like this would be your mass, volume, and solubility. And solubility can be further described in 3 ways. It can be unsaturated, saturated, or supersaturated. And note that your saturated and unsaturated, these two can both be homogeneous. Whereas supersaturated is the one that is going to be heterogeneous, because if it's supersaturated, this is where you're going to see your precipitation and crystallization. And you can further calculate these points using the conversion factors, which are either defined in your book on page 13 or in the Quizlet, or that'll be in the information that you'll get through experimentation like in lab. So going into solubility, we're going to do some problems, and this one is from your textbook. This was for number 56. So it says magnesium chloride is an important coagulant used in the precipitation of tofu from soy milk. Its solubility in water at 20 degrees is 54.6 grams. At 100 grams. And at 80 degrees, that solubility goes to 66.1 grams per 100. A mixture is made up of 16.2 grams of magnesium chloride and 38.2 grams of water at 28 degrees Celsius. So and the question is asking, in these conditions, is the mixture homogeneous? So to determine this, first thing is first is to start with the information that's most relevant to this problem. So this experiment is going to be done at 20 degrees Celsius, so you're going to use this first condition here and ignore the other one for now. Now you start with what you're given. So we start out with 38.2 grams of H2O. And now we use our conversion. We know that for every 100 grams of H2O, we can handle 54.6 grams of magnesium chloride. And when you calculate that across, you should get 20.85 grams of magnesium chloride. And since these are each 3 significant figures, that means this goes to 20.9 grams. And this is the amount that it takes for it to get to capacity or saturation. So now the next thing you do to answer the question is this a homogeneous mixture? And to answer that question, now you got to compare. This is what it can handle, and this is what you had put in. Since 16.2 is less than 20.9, that means it is unsaturated. And since it is unsaturated, that means yes, it is a homogeneous mixture. And the next part of the question asks, if it is homogeneous, how many more grams of magnesium chloride are required to make a saturated solution? So in order for it to be saturated, we need for it to exceed this 20.9 grams. So you're going to subtract the difference. So 20.9 minus 16.2, and that will give you 4.7 grams. So 4.7 grams of magnesium chloride. Oops, I was writing this down. Or what it would take to be saturated. Then in part B, it asks, how many more grams of magnesium chloride are needed to make a saturated solution at 8 degrees Celsius? So this is now going to be asking to perform an experiment at a different condition. So we're going to, again, set up our conversion factors. So we still start out with the same amount. We still start out with 38.2 grams of H2O. But now for every 100 grams of water, going back up here, you're going to use this condition. So for every 100 grams of water, we're now going to use that 66.1 grams. And that's going to get us 25.25 or 25.3 grams of magnesium chloride. And we're going to do the same thing. We know that it can handle this. And this is what we had put in 16.2. 16.2 is less than 25.3. Therefore, yes, it is again a homogeneous mixture. And if we are going to answer, the final question says, how many more grams are needed to make a saturated solution at this temperature? Again, you're going to subtract the difference. So 25.3 minus 16.2, that gives us 9.1. So for this part, 9.1 grams of magnesium chloride are what are needed at 80 degrees Celsius. Okay, and the next one we will do is number 60, that is also in your textbook. And that one's on page 21D. It says a supersaturated sugar solution of 650 grams of sugar in 150 grams of water is prepared to make rock candy. The solution is kept at 25 degrees Celsius, where we know that the solubility of the sugar is 220 grams per 100 grams of water. When we dip the string in, you make rock candy. How many grams of solid are obtained when the solution just reaches saturation? Okay, so the first thing we know is to in order for it to be supersaturated, the condition is that you will have 650 grams of sugar, which is and that's in 150 grams of H2O. And you also know at 25 degrees Celsius, the solution is soluble when it is 220 grams. And yeah, sugar, that's a little bit shorter, per 100 grams of H2O. So it's asking you to find how many grams will be that saturation point when it's in the 150, when we know this is a solubility in 100 grams. So to solve for that, first thing we do is take what we're given. And now you're going to apply the solubility conversion that we were given. You're going to calculate that across. And that is going to give you 330 grams of sugar. Next, you're going to take that total that you noted it is at supersaturation. You're going to subtract the 330 grams, where you know it's still soluble, and that is going to give you 320. That is the amount of grams of sugar that's needed just when the solution reaches saturation. Okay. Next, let's see here. Next, I'm also going to touch on something else that we can touch on stuff in the periodic table. Some of the things that you have covered. You have isotopes, isobars, and allotropes. Okay, so isotopes are different forms of the same element because they have the same atomic number, which in the atomic number, that's the name of protons or electrons. But they're different forms. So in the case of iodine isotopes would be this. So it's the same element. Okay, isobars, these are different elements that happen to have the same mass number. So this, an example of this would be if you had calcium, potassium, and chlorine, and all of them happen to have the same mass number. Oops. And allotropes, this is something different from the other two in that it's referring to the molecular structure of the element. So for oxygen, it's referring to how it'll occur as a diatomic or when it does this thing. So that's referring how it looks structurally. So that's the difference between those three. I believe on your quiz, you had a problem about this. Let me pull that up. Of course, I'm having trouble finding it. Okay. So if you were given she would give you the number of protons and number of neutrons, so you have to figure out what element it is by putting the pieces together. So you know that the number of protons is going to equal the number of electrons. So if there's 6 protons, and there's also going to be 6 electrons. And by using the number of protons, number of electrons, you are able to know the atomic number. So when you go to the periodic table, you're going to look for something that has the atomic number of 6, and that is going to be carbon. And then you're going to figure out, in order to put it in the right structural form, you need to figure out the mass number. And the mass number is by taking the number of protons and the number of neutrons together. So this is the form, this is the structural form for carbon as an isotope. Then just in general, when you're looking at the periodic table, that is going to be your atomic number. That is going to be atomic weight, mass number. Okay, all right. Next, we can touch on the one in your quiz, and that one was actually a combination of something that was in your textbook and that is also on your worksheet. So if you don't have your quiz with you, the actual graph that was the last question on your quiz, that is on page 21E. Looks something like this. And she had one substance B that was like this, and she had another substance A that I believe was like this. So that's how it looks in your textbook. And then she applied her own questions that are from worksheet number 1. And it was the one called Matter and Measurements Worksheet A. And on the back of it, this is where the idea comes from for this quiz. So if you understand how it was in the quiz, make sure you understand how it goes in the worksheet. For those of you that got this wrong in the quiz, after I walk through this, look over the one on the worksheet so you can know how it's asked in different ways. So this one goes, what is the maximum number of grams of substance B that 250 grams of water can dissolve in at 10 degrees Celsius? So given this graph, some of the things that you're given is that at 10 degrees Celsius is a max of 20 grams of substance per 100 grams of water. And you know that 10 degrees Celsius, again, you're given that 250 grams of water. So in order to do this, you're going to set up a conversion factor. So you know this is what you are given. I'm going to use different colors to keep things straight. So we start out with 250 grams of H2O. And we know that for 100 grams of H2O, we can handle 20 grams of substance B. And we get this from up here in the graph. So you look up here at substance B. And you saw that at like here was 20, and I believe here was 10. And you were told right here that all of your grams are in per 100 grams of H2O. So that's where the 100 comes from. So you calculate this across, and you will get 50 grams of substance B. And that's the max that you can handle at 10 degrees Celsius. And the second part asks if 33 grams of A is added to 55 grams of water, 100 degrees Celsius, will substance A crystallize? So if 33 grams is added to 55 grams of H2O, and all of this is done at 100 degrees Celsius, will it crystallize? Is it supersaturated? So first thing you're going to do is, again, calculate what you're given. So 55 grams of H2O. We know, again, per our chart, that for every 100 grams of H2O, and then going up to the chart again, here's substance A at 100 degrees Celsius. And when you multiply that across, this will give you 11. So 11 grams of substance A is what it can take at 100 degrees Celsius. So you do that part, and now you compare. 11 grams is what it can take, and 33 grams is what you added in. So now you take the difference. So you take 33 minus 11, and that gives you 22 grams of substance A that will crystallize. Okay, if you have any other questions, please feel free to email me or Dr. Wise. Since you do have an exam next week, if there is enough interest, I would not mind moving the SLA to a Tuesday or any day that you would more strongly prefer. Again, just let myself or Dr. Wise know. You have a wonderful day.